Humanity stands at a peculiar intersection of progress and pause. Today, we carry in our pockets computing power that far exceeds what once guided astronauts across nearly 400,000 kilometers of empty space to the moon. By every measurable standard, our tools are more precise, our simulations more accurate, and our understanding more complete. Yet, despite this extraordinary advancement, no human being has ventured beyond Earth's orbit in nearly half a century. This contrast invites a careful question, not a dramatic one. Have we somehow lost the ability to return to the moon? At first glance, it may appear so. After all, if something was achieved in the past, repeating it should be simpler with better technology. But this assumption rests on a misunderstanding of how complex systems function. Reaching the moon was never the product of a single invention or a fixed set of instructions. It was the outcome of a vast, interconnected system. Thousands of engineers, specialized manufacturers, testing facilities, and logistical networks operated in precise coordination. Think of it less as a machine and more as a living ecosystem, where each component depended on the presence and stability of others. A useful way to understand this is to consider a large orchestra. Even if every musician possesses exceptional skill, the performance depends on timing, coordination, and the continued existence of the entire ensemble. Remove enough instruments, and the symphony cannot simply be replayed from memory. The same principle applies here. The knowledge of how to go to the moon was never stored in a single place. It was distributed across people, processes, and physical infrastructure. When those elements begin to disappear, the capability itself becomes fragmented. A small but important teaching insight. In engineering, capability is not just about knowing what to do, it is about maintaining the environment that allows that knowledge to be applied reliably. So, the real issue is not that humanity forgot how to reach the moon. The deeper challenge lies in something less visible but far more significant. Over time, the system that once made such missions possible did not remain intact. As we move forward, the question shifts from knowledge to continuity. What exactly changed after those early missions concluded, and why did the foundation beneath them begin to fade? If capability depends on continuity, then we must examine what disrupted that continuity. The answer lies not in a single decision, but in a gradual withdrawal of commitment. During the height of the space race, the United States allocated nearly 4% of its federal budget to the effort of reaching the moon. This level of investment was not merely financial support, it sustained an entire industrial ecosystem operating at full intensity. Once the objective was achieved, the underlying motivation changed. The moon landing was no longer an urgent geopolitical priority. As a result, the system that had been carefully assembled began to dissolve. Factories that produced specialized components were shut down. Assembly lines, once optimized for precision manufacturing, were dismantled. Suppliers that provided highly specific materials and parts either shifted to other industries or ceased operations entirely. To understand the scale of this loss, consider a simple example. Imagine a manufacturing chain where one facility produces a unique alloy, another shapes it into components, and a third integrates it into a larger system. If even one link disappears, the entire chain becomes unusable. Recreating it is not as simple as restarting production. It requires rediscovering processes, retraining personnel, and rebuilding trust between independent contributors. NASA's strategic focus also shifted. With a reduced budget of approximately 0.5% of federal spending, attention moved toward low Earth orbit. Programs such as the Space Shuttle and the International Space Station emphasized sustainability and repeated access rather than deep space exploration. This transition was logical, but it came with a trade-off. The infrastructure required for lunar missions was no longer maintained. A useful teaching insight here is that complex engineering systems do not fail suddenly, they erode. Skills fade as experienced engineers retire. Documentation becomes outdated. Manufacturing tolerances, once understood through practice, lose their precision when not actively maintained. By the time interest in returning to the moon resurfaced, the original system no longer existed in a functional form. Engineers today are not simply continuing where Apollo ended, they are reconstructing a fragmented framework piece by piece, often without the benefit of the original industrial context. This leads us to a more intricate problem. Rebuilding something that once existed is not a matter of copying the past. It introduces new uncertainties, new constraints, and new points of failure. The question then is not why rebuilding is necessary, but why it has proven so difficult in practice. When a system is rebuilt after decades of discontinuity, instability is not an exception, it is the expected outcome. This is precisely what we observe as the modern lunar program begins to take shape. The process is no longer a continuation of a proven pipeline, but an active reconstruction under new conditions, where even small uncertainties can propagate into major delays. The first uncrewed Artemis mission provides a clear example. Multiple launch attempts were called off, not due to a single catastrophic flaw, but because of a series of technical inconsistencies. Engine sensors produced readings that could not be fully trusted. Liquid hydrogen, an extremely efficient yet difficult fuel to manage, presented persistent leakage issues. Each of these problems in isolation may appear manageable. In a tightly coupled system, however, they interact in unpredictable ways. To understand this, consider a simple engineering principle. When components operate near their performance limits, tolerances become extremely narrow. A minor sensor error is no longer a small inconvenience. It becomes a source of uncertainty that can compromise the entire decision-making process. Engineers are then faced with a difficult choice: proceed with incomplete confidence or delay and investigate further. External conditions add another layer of complexity. Unlike controlled laboratory environments, launch operations are exposed to real-world variables. Weather events, including hurricanes, can disrupt schedules, damage equipment, and force repeated resets of carefully timed procedures. Each delay introduces additional checks, recalibrations, and logistical adjustments. When the mission finally launched in 2022, the challenges did not end. During re-entry, the Orion capsule's heat shield displayed behavior that differed from predictions. Material was shed earlier than expected. Although internal temperatures remained within safe limits, the discrepancy could not be ignored. A useful teaching insight here is that engineering is not only about achieving success, it is about understanding why success occurs within safe margins. If a system performs correctly for reasons that are not fully understood, it introduces risk for future missions. This single anomaly required engineers to revisit models, test assumptions, and re-evaluate safety thresholds. The objective is not merely to replicate a successful flight, but to ensure that every parameter behaves predictably under known conditions. What emerges from this phase is a pattern. Rebuilding capability introduces layers of uncertainty that must be resolved one by one. And in such an environment, even the smallest unresolved question has the potential to delay progress significantly. What begins to emerge from these repeated uncertainties is a shift in philosophy. Earlier programs operated under intense pressure to achieve results quickly. Today, the constraint is different. The defining principle is not speed, but absolute reliability. In practical terms, this means that every system must function correctly, not just once, but under every foreseeable condition. This is why Artemis operates under a strict and uncompromising standard. Human missions introduce a level of consequence that leaves no room for partial understanding. A system that works most of the time is, in this context, a system that is not yet ready. This approach has had visible effects on the mission timeline. The Artemis II crewed flight, initially targeted earlier in the decade, has been pushed to 2026. These delays are not arbitrary. They reflect unresolved technical questions that must be addressed before human lives are placed at risk. Consider the role of life support systems. These are not auxiliary components. They form a closed environment where oxygen, temperature, and pressure must remain stable over extended periods. Even minor inefficiencies can accumulate into serious hazards. Upgrading and validating these systems requires careful testing under conditions that closely simulate real missions. Another example lies in the helium pressurization system. At first glance, helium may appear to be a minor element in rocket design. In reality, it performs a critical function. It maintains pressure within fuel tanks, ensuring that propellants flow consistently into the engines. If this pressure fluctuates or fails, combustion becomes unstable, and the entire propulsion system is compromised. A useful teaching insight here is that in complex systems, supporting components often carry equal importance to primary ones. The failure of a small subsystem can cascade into a complete mission failure, not because it is large, but because it is essential. NASA's current strategy reflects this understanding. Launches are not fixed commitments. They are conditional events, dependent on the readiness of every subsystem. If a single parameter remains uncertain, the launch is delayed. This may appear cautious, but it is a rational response to the scale of risk involved. The consequence of failure extends beyond a single mission. A catastrophic event could halt progress for years, not only due to technical setbacks, but also because of loss of confidence and increased scrutiny. As a result, progress becomes deliberate and measured. Each delay is, in effect, an investment in certainty. And this cautious progression prepares us for the next layer of difficulty, where the environment itself introduces dangers that no engineering system can fully eliminate. As engineering challenges are gradually reduced through careful testing and validation, a different category of difficulty begins to dominate. This is not a problem of machinery or design, but of environment. Beyond the boundary of low Earth orbit, conditions change in ways that no engineering system can fully neutralize. In orbit around Earth, astronauts operate within the protection of the planet's magnetosphere. This invisible field deflects a large portion of harmful radiation, acting as a natural shield. It is not perfect, but it reduces exposure to levels that can be managed over time. Once a spacecraft moves beyond this region, that protection rapidly diminishes. The primary concern in deep space is galactic cosmic radiation. These are high-energy particles originating from distant astrophysical events, including supernova explosions. They travel across the galaxy at near-light speeds, carrying enough energy to penetrate both spacecraft materials and human tissue. To understand the significance of this, consider the difference between surface-level exposure and internal disruption. Unlike conventional radiation, which may be partially absorbed or deflected, these particles can pass through the body, interacting directly with cells. This interaction can damage DNA, increasing the probability of long-term health effects such as cancer and degenerative diseases. A useful teaching insight here is that radiation risk is cumulative. It is not defined by a single event, but by total exposure over time. Even small amounts, when sustained, can produce measurable biological impact. Spacecraft design can mitigate some of this risk through shielding. However, effective shielding against high-energy particles requires materials that are either very dense or specifically structured, both of which introduce significant trade-offs in weight and cost. Increasing protection often means increasing mass, which in turn affects launch capability and mission efficiency. This creates a constraint that cannot be easily resolved. Engineers must balance protection with feasibility, ensuring that astronauts are not exposed to unacceptable risk while still maintaining a functional mission architecture. Deep space, therefore, is not simply an extension of the environment near Earth. It is fundamentally different. It is an active field of radiation where exposure is constant and unavoidable. As missions extend further and durations increase, this challenge becomes more critical. And while cosmic radiation represents a persistent background threat, it is not the only source of danger. There exists another, far less predictable hazard, originating much closer to home. Alongside the constant exposure to cosmic radiation, there exists a second hazard that is far more immediate and far less predictable. Unlike distant astrophysical sources, this threat originates from our own star. The Sun, while essential for life on Earth, can become a source of intense and sudden danger in deep space. At irregular intervals, the Sun releases bursts of energy known as coronal mass ejections. These events eject vast quantities of charged particles into space at extremely high speeds. When directed toward a spacecraft, they can significantly increase radiation levels within a short period of time. The key difference here is timescale. Galactic cosmic radiation accumulates gradually, allowing for long-term management strategies. Solar events, in contrast, can escalate within hours. This leaves limited time for detection, decision-making, and protective action. To understand the seriousness of this, consider the effect of concentrated exposure. A sufficiently strong solar event can deliver radiation doses that exceed safe limits in a matter of hours rather than years. This transforms the problem from one of long-term risk into an immediate survival challenge. Current spacecraft design addresses this constraint in a practical, though not entirely sophisticated manner. The Orion capsule incorporates a designated area with relatively higher shielding. In the event of a solar storm, astronauts are instructed to gather in this confined space. What is particularly instructive is the method used to enhance protection. Instead of relying solely on specialized shielding materials, astronauts use available resources such as water containers, food supplies, and onboard equipment to create an additional barrier. These materials, due to their density and composition, can absorb a portion of the incoming radiation. A useful teaching insight here is that effective solutions in constrained environments often rely on reusing existing resources rather than introducing entirely new systems. This approach reduces complexity while providing a measurable improvement in safety. However, this strategy also highlights a limitation. It is not a complete solution but a mitigation technique. It reduces exposure rather than eliminating it. The unpredictability of solar activity means that astronauts must remain prepared for events that cannot be precisely forecast. As missions extend in duration and distance, reliance on such interim measures becomes increasingly challenging. The environment does not adapt to human presence. Instead, human systems must continuously adapt to environmental uncertainty. And while radiation presents both persistent and sudden threats, there is another dimension of space travel that operates more quietly, yet affects every moment of a mission. It is not external, but internal to the human body itself. While external hazards such as radiation demand constant vigilance, there is a quieter transformation taking place within the human body itself. This transformation does not arrive suddenly, nor does it depend on rare events. It begins almost immediately after entering microgravity and continues for as long as the environment persists. On Earth, the human body operates under continuous gravitational load. Muscles work to support posture, and bones maintain density through regular mechanical stress. Remove this load, and the body begins to adapt in ways that are efficient in space, but problematic upon return. In microgravity, muscles no longer need to support body weight. As a result, they gradually weaken through a process known as atrophy. At the same time, bones begin to lose mineral density, particularly in load-bearing regions such as the spine and legs. This loss occurs because the biological signals that regulate bone maintenance depend on mechanical stress, which is now absent. To understand the scale of this change, consider a simple comparison. A person confined to bed rest on Earth for extended periods experiences similar effects, including muscle loss and bone weakening. In space, however, this process occurs more rapidly and more uniformly across the body. A useful teaching insight here is that the human body is highly adaptive, but not always in ways that align with mission requirements. It optimizes for the current environment, even if that optimization creates challenges later. To counter these effects, astronauts follow strict daily exercise routines. Specialized resistance devices are used to simulate weight-bearing activity. These systems are carefully designed to provide controlled force without relying on gravity. Despite this, the countermeasures are not perfect. They reduce degradation but do not eliminate it. Even relatively short missions require continuous effort. A duration of 10 days is sufficient to produce measurable physiological changes. Over longer missions, the cumulative effects become more pronounced, influencing mobility, strength, and recovery after return to Earth. This introduces an important constraint for mission planning. Human capability in space is not static. It evolves over time, and not always in a favorable direction. Engineers and medical teams must account for these changes when designing mission duration, workload, and recovery protocols. As we consider these biological limitations alongside environmental risks, a broader question begins to take shape. Given the complexity, the cost, and the persistent danger, why continue at all? What justifies extending human presence into such a demanding domain? The question of why we continue despite these risks leads directly to a shift in how space exploration is being approached. The objective is no longer limited to short-duration missions or symbolic achievements. Instead, the focus has moved toward establishing a sustained and repeatable human presence beyond Earth. This is where the concept of lunar infrastructure becomes essential. Rather than treating each mission as an isolated event, current plans aim to create a system that supports continuous operation. In practical terms, this requires intermediate platforms, reliable transport pathways, and stable points of coordination. One of the central components of this system is the Gateway Station. Positioned in orbit around the Moon, it is designed to function as a staging node. Spacecraft arriving from Earth can dock, transfer crew and supplies, and prepare for descent to the lunar surface. This reduces the need for each mission to carry all resources directly from Earth, improving flexibility and efficiency. To understand its role, consider a logistical analogy. Long-distance travel on Earth often depends on hubs, such as ports or airports, where resources are redistributed. Gateway serves a similar function in space. It separates the journey into manageable segments, each optimized for specific conditions. From this orbital platform, astronauts will transfer to specialized lunar landers. These vehicles are designed specifically for the conditions of the Moon, including its lower gravity and lack of atmosphere. This division of roles allows each system to be optimized rather than forcing a single vehicle to handle all phases of the mission. Future plans extend this structure further. Missions are expected to target the Moon's south pole, a region of particular interest due to its environmental conditions and potential resources. Establishing a base camp in this area introduces the possibility of longer stays, repeated missions, and continuous scientific activity. A useful teaching insight here is that sustainability in complex systems is achieved through modular design. By dividing functions across multiple components, the system becomes more adaptable and easier to maintain over time. This approach represents a fundamental transition. Exploration is no longer defined by reaching a destination once. It is defined by the ability to operate there consistently. As this infrastructure begins to take shape, its purpose becomes clearer. The Moon is not the final objective. It is a testing ground, a proving environment where systems, technologies, and human capabilities can be refined. And this leads to the next logical question. If the Moon is a step, then what lies beyond it? And why is this intermediate stage considered essential for reaching it? If the Moon serves as a testing ground, its value lies not only in location but in what it contains. Among its most significant resources is water ice preserved in permanently shadowed craters near the poles. These regions never receive direct sunlight, allowing ice to remain stable over geological timescales. This resource has practical implications. Water can be separated into oxygen and hydrogen. Oxygen supports breathing, while hydrogen, when combined with oxygen, forms an efficient rocket propellant. In effect, the Moon offers the possibility of producing both life support and fuel locally. A useful teaching insight here is that transporting mass in space is extremely costly. Every kilogram launched from Earth requires significant energy. By generating resources on the Moon, missions can reduce this burden and extend their operational range. This transforms the Moon from a destination into a supply point. It becomes a place where missions can refuel, prepare, and expand further into space. However, this shift introduces a new layer of responsibility. Extracting and using these resources is not without consequence, and it raises important questions about how such activities may alter the lunar environment itself. As we consider the Moon as a source of resources, we must also examine the consequences of using it. Large-scale operations introduce disturbances that cannot be easily reversed. When powerful landers descend, their exhaust can spread across the surface, potentially altering or contaminating regions that have remained undisturbed for billions of years. One area of concern is the preservation of water ice. These deposits are not only useful resources but also scientific records. They may contain information about the early solar system. If contaminated, that information could be permanently lost. Lunar dust presents another challenge. Unlike Earth's soil, it is sharp and abrasive. It can damage equipment and pose risks to human health. Managing this material requires careful design and operational discipline. A useful teaching insight here is that exploration often changes the very environment it seeks to study. This creates a balance between utilization and preservation. The Moon, therefore, is not just a destination, it is a laboratory. Altering it may limit our ability to answer fundamental scientific questions. Yet, progress requires measured risk. The Artemis program represents a step forward, not because it is perfect, but because it allows us to test, learn, and improve. In doing so, it prepares humanity for a far more demanding objective that lies beyond the Moon.